This section is about the chain rule, and the chain rule is very similar to what we did before, but instead of um, just working on equations, we're working with variables. So let's look at the chain rule. There are a couple cases here. So let's start with case one, where in case one, z is equal to f of xy, which is a differentiable function, and x is equal to a function in terms of t, and y is equal to a function in terms of t. Both are differentiable functions of t. Now this is case one because you only have one, you have multivariables for z, but in terms of x and y, you only have a single variable. So when you look at this, the chain rule is very similar to where we've done it in other polar and in parametric equations. So we're going to take the derivative of z with respect to t to be the partial of f with respect to x times dx over dt plus the partial of f with respect to y times the derivative of y with respect to t. So it's not too difficult and it doesn't change a whole lot. It's just we're working in lots of variables. So let's look at a specific example. And it says let z equal x squared y plus 3xy to the fourth, where x equals sine 2t and y equals cosine t. So I'm going to write out the chain rule, and it says dz over dt equals the partial of z or f with respect to x times the derivative of x with respect to t plus the partial of z with respect to y times dy, the derivative of y with respect to t. Okay, so we're going to take the derivative of z with respect to t to be equal to. So we're going to take the derivative of all of this with respect to x. So that would be 2, I'm going to put parentheses, 2xy plus the derivative of 3x is just 3y to the fourth times the derivative of x with respect to t. The derivative of sine of something is cosine of the same thing, and the derivative of 2t is 2. So that handles that part. Now let's talk about the y. So we're going to take the partial of z with respect to y. We're going back up here. So we're going to keep the x squared, and the derivative of y is 1, plus y to the fourth becomes 4y to the third. So we have 12xy to the third. And the derivative of y, the derivative of cosine, is negative sine of t. So we're going to rewrite it, not much, because you don't really want to distribute this mess. That's a lot of variables happening. So we're just going to rewrite it like this. And this would be minus x squared plus 12xy to the third times sine of t. So the chain rule isn't overly hard. It's just making sure that you catch all the pieces of it. Let's look at one more. Let's call this natural log of x squared plus y squared plus z squared to the 1/2 power. Okay, so the directions say find dw over dt. So we're going to take the derivative of w to be the derivative of natural log of something is 1 over the something. I'm going to write it pretty with the square root in it. Since we're taking that partial derivative with respect to x, we're going to keep that in mind. We're going to say times the derivative of something to the 1/2 is 1/2 times something to the minus 1/2 times the derivative of the inside would be 2x because you're taking your derivative with respect to x. So all of that is the partial derivative with respect to x. And now for the chain rule, you got to take the derivative of x with respect to t. So the derivative of sine of something is cosine of that. Plus the derivative of natural log of something with respect to y is 1 over the something. And the derivative of the parentheses to the 1/2 is 1/2 to parentheses to the minus 1/2. And the derivative with respect to y is 2y. And the derivative of the equation y with respect to t, the derivative of cosine is negative sine of t. Plus, we're doing the derivative with respect to z. So we have 1 over the square root of x squared plus y squared plus z squared times 1/2 times x squared plus y squared plus z squared to the minus 1/2 times 2z, and the derivative of tangent is secant squared. So now let's clean this up. The 2, let's go back up here. This 2 cancels with this 1/2. And this is a negative 1/2, and we have a denominator with the square root, so that becomes a squared. So let's say dw over dt equals, the denominator becomes x squared plus y squared plus z squared. And on the top, on this one, we have x cosine of t. And then we have a minus on the next one way over here. So the 2 and the 1/2 cancel. And the denominator again is x squared plus y squared plus z squared. And the numerator will be y times sine. So we have y sine of t plus the 2 and the 1/2 cancel. The denominator is x squared plus y squared plus z squared. And the numerator is z times secant squared t. So that's our partial derivative. Now, since they have common denominators, we could go one more space and say dw over dt equals x squared plus y squared plus z squared. We have x cosine of t minus y sine of t plus z secant squared of t. So nice pretty answer. This is case 2 of a chain rule. Notice that we have 2 sets of answers here, because when you start this chain rule, let's look at the fact that z is in terms of 2 variables, and x is in terms of 2 variables, and y is in terms of the same 2 variables. So here we're going to do the partial of z with respect to s and the partial of z with respect to t. So in the first one, you're going to take the partial of z with respect to x and then the partial of x with respect to s, plus the partial of z with respect to y times the partial of z of y with respect to s. And similarly in the second one. So let's look at what this looks like. We're going to let z equal e to the x sine y, where x is equal to st squared and y is equal to s squared t. Now they only ask us to find the partial of z with find both. The partial of z with respect to s and the partial of z with respect to t. So let's start with the partial of z with respect to s. So we're going to say the partial of z with respect to s is equal to, now you're going to take the derivative of this with respect to x. So the derivative of e to the x is e to the x, and sine y is a constant. And then we're going to multiply it by the derivative of x with respect to s. So the derivative of s is 1, and we just get t squared. So that doesn't work out too badly. Now we're going to go back to z and find the partial derivative with respect to y. So we're going to keep the e to the x, and the derivative of sine of y is cosine of y, times, and we're going to come over here and take the derivative of t to be 1. I'm sorry, we're doing the derivative with respect to s. The derivative with respect to s is 2s. Let's make sure those don't get absorbed into the cosine. So we're going to rewrite this to be the partial of z with respect to s equals t squared e to the x sine y plus 2s e to the x cosine y. It's not too bad. It kind of makes sense when you think about all the things going on. There's a pretty proof for it in your book. You're welcome to check that out. So now let's look at the second one. So this is our first answer. So now let's do the partial of z with respect to t equals, so we're going to start with the derivative of z. with respect to x is again e to the x sine y. And the derivative of x with respect to t is 2t, and you keep the s, plus the derivative of e to the of z with respect to y. You keep the e to the x, and the derivative of sine y is cosine of y. And then we take the derivative of y with respect to t, so we have 2s. So then our final answer for this part, the partial of z with respect to t, is equal to 2st e to the x sine y plus 2s e to the x cosine y. So they're not too difficult. The problem is there's a lot going on. So they use what they call the tree method. If you start with z, we can take the partial derivatives with respect to x and y. So this is the partial of z with respect to y, and the partial of z with respect to x. And from there, you have two partial derivatives. So you have the partial of x with respect to s, and the partial of x with respect to t. And then for the y, we have two derivatives as well. So we're going to go to s and to t. So we have the partial of y with respect to s and the partial of y with respect to t. So if you draw a tree diagram, it will help you to be able to find all of your chain rule pieces. So you can follow the branch down. So if you're finding the partial of z with respect to s, you're going to start with this one and then this one. So it makes sense. S and t are your independent variables. X and y are called intermediate variables. S and t are your independent variables, which we're used to, but x and y are now called your intermediate variables. Intermediate. And it makes sense because they're the intermediate variables. And then z is called your dependent variable. So I believe that makes sense. And this is your chain rule general version. So no matter how many variables you have, for your intermediary, you just take each one and then with respect to t or s or whatever you're given. So you're going to have a bunch of these, and the n's represent your independent variables. So that tells you how many terms you're going to have in your chain rule answer. And then you have your independent variables, s or t, and however many of those you have, that's how many equations you're going to have. So an example of how we see this is without even doing a whole lot of math, we're just going to do a tree diagram. So this one says to write out the chain rule for the case where w equals the function in terms of x, y, z, and t, and x, y, z, and t are all in terms of t and u. So let's start with the w up here. If you build your tree diagram, it will help you do this easily. So my w is going to have 4 branches. All right, so we start. And then z, and then t. And x breaks down into u and v, and y breaks down into u and v, and z is going to break down into u and v, and z is going to be u and v. So you're supposed to write the partials in there. So we're going to trace this path right here and say the partial of w with respect to u is equal to the partial of, maybe when you make a mistake, you should write it on, right? The partial of w with respect to x and the partial of x with respect to u. So we have the partial of w with respect to x times the partial of x with respect to u. Plus, we're going to travel down the u path. We have the partial of w with respect to y times the partial of y with respect to u. Plus, the partial of w with respect to z times the partial of z with respect to u. Plus, the partial of w with respect to t times the partial of t with respect to u. So that would be our first chain rule answer. And now we need to do it in terms of v. So we're going to do the same thing again in terms of v. So we're going to go to the partial of w with respect to v is the partial of w with respect to x times the partial of x with respect to v, plus the partial of w with respect to y times the partial of y with respect to v. So it travels down this path. And then we're going to do the partial of w with respect to z times the partial of z with respect to v, plus the last one is the partial of w with respect to t times the partial of t with respect to v. So it helps you write out your chain rule setup, which is very helpful. You should write it out before you do a problem. So let's look at a problem. Okay, we're asked to find the partial of u with respect to s. And we're given u in terms of x, y, and z. And x, y, and z are all in terms of r, s, and t. So let's build. We start with u, and u has three values here, x, y, and z. And then x has three values, r, s, and t. And y has three values, r, s, and t. And z has three values, r, s, and t. But we're only finding the partial with respect to s. So that's this one. So we're going to say the partial of u with respect to s is equal to the partial of u with respect to x times the partial of x with respect to s, plus the partial of u with respect to y times the partial of y with respect to s, plus, let's move this just a little bit, the partial of u with respect to z times the partial of z with respect to s. So we don't have to find all three of the partial derivatives. We just have to find the one with respect to s. So we're going to say the partial of u with respect to s is equal to the partial of u with respect to x is, we're going to take this derivative to be 4x to the third y, plus, those are neither one x, so we're done. And then the partial of x with respect to s. So we just have r e to the t, plus the partial of u with respect to y. So we're going to come back to this with respect to y. And we keep the x to the fourth, and y is 1, plus 2yz to the third, times, now we're going to take the derivative of y with respect to s. And when we do this, s squared becomes 2s. So we have 2rs e to the minus t. Squeeze that in there. And then we're going to say plus, we're going to go back to the u and take the derivative with respect to z. The first term is 0. The second term, the derivative of z to the third is 3z squared. So we get 3y squared z squared. And the derivative of z with respect to s is 1. So we get r squared sine t. So that means that's our partial with respect to, our partial of u with respect to s. We could make it pretty, but I think that's a fine answer. You could remove the parentheses on the pink term and the green term, but it doesn't really affect it. So now let's talk about when r equals, let's use these values here. When r equals these values, then we say the partial of u with respect to s is going to be, notice that we have x, y, r's, e's to the t's. So we're going to need x and y. So let's go ahead and figure out x. X is 2 times 1 times e to the 0, which is 1, so x is 2. Y is 2 times 1 times e to the 0, so y is 2. And z is 2 squared, which is 4, times 1 times sine of 0, which is 0. So now we can plug these values in and we get 4. I'm going to color code them and match what we did above. So we're going to say 4 times x to the third is 8, times y, which is 2. And then we have r, which is 2, times e to the t, which is 1, plus x to the fourth is 16, plus 2 times y, which is 2, times z to the third, which is 0. And then we have 2 times r is 2, s is 1, and e to the net to the 0 is 1, plus 3 times y squared is 4, times z squared is 0, and r squared is 4 times 0. So that's 0. So we get our partial of u with respect to s is equal to 32 times 2 is 64, times 2 is 128, plus 16 times 0, 16 plus 0 is 16, and we have 2 times 2 times 1 times 1. So we have 16 times 4 is 64. So this gives me 192. And I don't think this lesson is too hard. I hope that you enjoy it. Have a great day.